Afternoon, everyone. So, great to be here in Kansas City. I'm not from Kansas City, you can probably tell. My name's Joe. I am going to introduce myself on the next slide because not many of us know each other. But this is what I'm going to be talking about. So, a piece of research from my team over in the UK, looking at some aircraft fire safety. We are a generalist kind of fire safety research organisation and consultancy. I am founder and chief exec of the business, but I'm very much a hands-on chief exec, so I'm head of R&D, head of our engineering consultancy, and chief instructor at our training business. I kind of collect job titles, as you can see. I'm also vice president of the IFE Southern Branch. What I'm here to talk to you about today, though, is to present some research that some of my team have done, and I must shout them out for this. So, Joel, Chris, Jack, Renee, Kirsty, who's at the back, and myself. It's a collaboration between a bunch of my team. Based on the complexity, you might see why a few of us have inputted, and this is a very quick run through of a much larger piece of work, so I'll try and get through as much of it as I can. What we've been looking at in this piece of work is looking at safe escape times from aircraft, and we're looking at short-range aircraft, specifically the Boeing 737-800. Now, the reason we're looking at that type of aircraft is not because it's special or unique in any way. In a previous role, I used to be head of fire safety for an airline, and I used to look after 100 of these. Our fleet had 100 737-800s in it, and it was my job to keep them not on fire, shall we say. So a big part of my role was investigating this. Now I've got a bit more time on my hands, because I'm no longer head of fire safety at an airline, thankfully. And I have a team around me. We're now investing a lot of our time and resource into this field. So this particular piece of work we've done here, first of all, we are looking at how long, first of all, it takes to evacuate from an aircraft. And secondly, what conditions we might have inside that aircraft if that fire happens during flight inside the passenger cabin. We've gone about this through modelling in FDS. We've used PyroSim to build the models. We've run a lot of tests on this. There is a full paper that sits behind this, and I'm going to talk through just one particular aspect this afternoon. We've used the ASET RSET methodology. We've seen that a couple of times today. I think certainly in the UK we know it as bread and butter. I think it's universal. We all sort of understand that. So I won't teach it to us today, but I'll describe it a bit so you understand why we've adopted that. We've built a geometrically accurate model of a 737. We actually built every different aspect of it, and we can use different areas. So we can look at the cockpit, we can look at the flight deck, we can look at the cargo hold, the wings and everything. I've got some images in here of what that looks like. We've done various fire scenarios, and we've benchmarked against this standard that we have of 90 seconds to evacuate an aircraft. I'll come on to talk a bit more about that when we get into the talk. So, anyone that's seen me speak before, probably not many of you to be fair actually, if I was in London it'd be a slightly different story. I always start my talks by focusing the mind. I try and talk about case studies wherever I can. I'm also a lecturer at a university in the UK. I teach fire engineering, undergrad and postgraduate level up to PhD level in fact, and this is very common for me. I always try and get us focused on why we care. Why do we care, Joe, is the question I always ask. A couple of key case studies for us in 737 aircraft and aircraft fire safety generally. This one here first. A fire that happened in 2019, I remember this happening. There were 41 fatalities, unfortunately, on this particular incident. What happened here is that the aircraft took off from Moscow. It was struck by lightning and it had to divert. The fire itself happened as the plane landed. It was above its safe landing weight because it was still filled with fuel, because it had to very quickly turn around. Fire happened, full evacuation took place, but unfortunately there were a number of fatalities. I'm going through super quick, but the notes are here. If anybody wants them after, do drop me a message. Another fire here. This is to highlight different types of fire we might encounter on aircraft. This is a really notable case study for anybody that works in aviation or anybody that works in fire, looking at infrastructure case studies. In this particular event in Taiwan, there were two things in the overhead bin, the overhead locker, that were being transported at the same time. There was a sealed bottle containing petrol, and there was also a motorbike battery, both being carried by the same passenger. The aircraft, whilst it was taxiing, encountered some turbulence, so it was a hard landing, and these two things interacted. There was a fuel spillage, the vessel was cracked, vapor cloud formed, battery shorted, and a fire happened in the overhead bin. This was one of the more important ones for us. The image at the bottom there is really indicative of what we're investigating in the talk I'll come on to. A couple more quick examples, just of, again, the types of fires we might encounter with aircraft and what we might be trying to design against. This was a fire at Glasgow Airport. This was a Jet 2 aircraft. I used to be head of fire safety at the particular airline. This was before my time, but this is one that was talked about a lot in the office when this happened. Aircraft was taking off. This was a 737-800 aircraft. Again, we had 110 of these at the peak while I was in post. During takeoff, there was a smell of smoke and there was some misting identified by everyone on board. So they decided to abort the landing, stop the aircraft, stop taxiing, and began an evacuation. The misting kind of subsided and the smell became less strange, so people didn't panic too much. Everybody stopped and grabbed their bags, evacuated very slowly. It took about 3.5 minutes to evacuate. That number becomes important. You'll see why we're interested in that. And a final one before we get into some technicals, more severe, aircraft here, 1988, the Swiss Air Flight 111 took off. There was an in-flight fire that caused a crash. An in-flight passenger cabin fire that leads secondarily to a crash is a huge case study for us investigating these types of incident. So just a couple of examples. When I teach at the university, I've got about 20 of these. It goes on for about an hour. I've saved you guys that. And this big clock in front of me tells me I've done it in about 4 minutes. Good work, Joe. So, moving on to talk a bit more about the aircraft we're interested in. 737-800, very common to us in the UK. If you fly over to anywhere in Europe short haul, we've probably flown on one of these. I think I flew on one on Saturday, over to Amsterdam before I came to Kansas City. Really popular in the US as well. It was the most mass-produced aircraft until 2019 when it was overtaken. The image we see on the top there is fairly indicative. On a 737-800, we don't normally split out into different classes. You'd stand at the rear of the aircraft and you'd look right the way down to the cockpit at the front. 189 seats, 189 passengers with cabin crew involved and flight crew. You're looking at about 190, maybe the thick end of 200 people. Really long tunnel, simplest way of putting it. Everything else is separated out. The cockpit, the flight deck is a compartment wall. Cargo hold is a compartment wall. Wings, tail, separate. So we're just looking at a big long tunnel. Here's what it looks like on a seat map. So as I say, 189 generally. It's worth noting that these aircraft are very easy to strip out and reduce the numbers. This is the peak you'd get in there. We used to have an aircraft that we kept specifically for football teams, beg your pardon, soccer teams, that we would use to Manchester United, Manchester City. We'd strip out the seats and we'd put 20 in if they're flying around Europe. Very easy to reduce the occupancy. You can't really go above this. You wouldn't put more than 200 on an aircraft like this. They do always have, though, 32 rows. Very linear seating. The seats come as one unit of 3 seats. You can pop those in and out. And you've got 8 emergency exits. I feel like cabin crew suddenly. 2 at the back, 4 over wing, and 2 at the front as well. And they don't move, they don't change. So for us, in terms of safety, we've got some nice fixed parameters. Unlike when we design buildings and we know the buildings might change during the occupancy. Quick note on the fire safety we have before we come on to our modelling and what we've been looking at. Generally speaking, smoke detection in aircraft like this, only in the bathrooms and the cargo hold. A fire that happens in the main cabin, we anticipate would be picked up by a passenger, or we would otherwise see or smell it. Suppression systems we have again in the cargo hold, and we have sometimes in the bathrooms. When I was working at the airline, we took them out because they're expensive and heavy, but sometimes in the bathrooms. And in the APU, the auxiliary power unit, which is the bit in the tail. Other than that, that's broadly what we put in for fire safety in these aircraft. A key thing, something that becomes really important in our work that I'm presenting here and in the much wider paper, there's a lot of discussion on it, is ventilation. So in these aircraft, again, when I got on at Manchester Airport on Saturday, or Friday, or whenever it was I was flying, you turn the thing above the seat that gives you the ventilation. So a constant ventilation cycle in narrow-body aircraft like this is drawing in air at low level, recirculating it, filtering it, and dumping it in from above. And that's the thing that you turn. Now that runs as a continuous cycle. That never stops. There's no shut-off like we'd have in a building where all your AC would turn off with the fire. That's a continuous cycle that we became really interested in our findings. Now, okay, so what standards we design these aircraft to? It's this number here, it's 90 seconds. The CAA and the FAA have the exact same standard. You must be able to evacuate an aircraft within 90 seconds. If you have more than 44 passengers, that's your benchmark. It's always 90 seconds. Now, I went to a conference a few years ago in Mallorca, and I was speaking to all the other heads of all the other airlines. We were talking about how well we'd done, and we all agreed that this number is very easy to achieve. But the reason it's very easy to achieve is because we don't use passengers. We use our cabin crew and our flight crew, and there's not a real fire. Very easy benchmark. And I became interested in this because a lot of my research is based around the standards we use. I'm a performance-based design engineer. I'm not somebody that generally follows prescriptive guidance. So when I see a number, I shoot for it and I try and investigate it a little bit more. So having a background in building design and performance-based design, I apply my ASET RSET model, as we've got on screen there. We are all pretty universally well-versed in this, I think. Some nods. Everyone's nodding. Good. Our 90 seconds is essentially our RSET, the time it takes to evacuate. And within that 90 seconds, because it's in our FAA and CAA standards, we expect there's a margin of safety implicit in that. So if I was doing performance-based design, that 90 seconds is the time for everybody to get out the aircraft. So I put my engineering hat on and became interested in my ASET. Is that greater than, less than, or equal to 90? What are the conditions like after 90 seconds if it's not a runway at Leeds Bradford Airport filled with my own staff? What if this is Glasgow Airport, where it took 3.5 minutes, and we know that, we have CCTV footage. So we sought in this study to quantify the ASET, quantify the conditions, look at the conditions we have after 90 seconds in a real fire, or at least in a simulated fire, in as close to a real environment as we can. So, where we got to with this. FDS is our bread and butter, of course. This is what we're using. We are performance-based engineers. We use PyroSim to construct our geometrically accurate 737 geometry. It looks like that. That's without the cockpit on, but we do have the cockpit, and we turn these bits on and off depending on what we're investigating. We've done some engine fire modelling. We've done some modelling of the cargo bay. We've done the cabin. We've done all the different areas. For this one, we're only interested in our main cabin. It looks something like this. One of my guys put this together. He was very clever about it, actually. I thought he kind of broke it down into the 32 rows. He built each row and multiplied it out. Nice little bit of rationalisation for himself there. And we ended up with a nice, geometrically accurate, materially accurate as well. The seating has the correct seat cushion materials. The overhead bins contain plastics that we'd taken from literature that we obtained. This is all data we had available to us. We ended up with a nice, geometrically accurate model. Going through some of the scenarios. The case studies highlight that there are any number of scenarios, as we'd expect in any modelling, really. We're all familiar with this. But some of the key things we were interested in were, first of all, what if the fire happens in the overhead bin, as we saw in Taiwan? And secondly, what if the fire happens underneath the seat or is indeed on the seat? Because, of course, when you get on an aircraft these days, you put some stuff in the overhead bin and some under the seat in front. So we became interested in what might happen in those different locations. That was our first variable. And our second variable, we were interested in the ventilation. If it's just that air conditioning running, and secondly, what happens if the doors open? Now, the doors opening in an aircraft is something that only happens when it's on the floor, says the expert in aviation safety. Probably all knew that anyway. But we're modelling here that we are evacuating on an apron. So we've opened and closed the doors as we would do in a building model. Completely not included in our prescriptive codes, but important to us here. Just to highlight very quickly for a few seconds what these look like. If you look at a seat map, case one, we've got a fire at the front of the aircraft, underneath the seat with air conditioning running only. Case two, we've shifted it over to the centre of the aircraft. This is actually really important. I've not really got too much time to do this, but it's important where the fire is, because the recirculation of the aircraft spirals through the aircraft from the front to the back. So as it's recirculating, it's not recirculating just in the ring that you sit in. You are breathing in row one if you're in row two. And if you're in row three, you're breathing in row two. I've never said it like that, but every time I do this talk now and I'm saying it like that, you're breathing in the passengers in front of you. Enough said, the better. Move on, Joe. Case studies 5, 6, 7, 8, as you can see, they're mapped out exactly as they are. We're obviously not opening the doors next to where the fire is. So case 6, for example, the 4 overwing exits are not going to be opening because no one's going to be evacuating, so we get slightly less ventilation. Some of the outputs we're looking at, temperature, visibility, velocity, toxicity, pressure. We gave up on pressure. Read the full paper to find out why. Lots of passive aggression in there. But we were really interested in temperature and toxicity. We sort of knew what was coming. So to skip through, these are just a few slides and I'll get onto the actual results. This is fire underneath the seat in the centre of the aircraft, row 15. As we anticipate, we're getting smoke rise to form a smoke layer. That smoke layer doesn't last very long at all. Reason for that is it recirculates, dilutes. We very quickly, in these cases, lose tenability because of both visibility and toxicity. That continues front to back of the aircraft, and we very quickly, spoiler alert, before we get to results, lose tenability. Toxicity matches visibility. Again, very quickly we get a smoke layer form and then dissipate downwards. So it dilutes itself with our air conditioning continuing to run, and we run into an issue with toxicity. Temperature in the last 37 seconds of the talk, broadly the same. Let me get to the full results because I really want to touch on this. Is the ASET greater than, less than, or equal to 90? We discovered in 3 of our really simple cases it's less than. Essentially, we lose tenability in less than the 90 seconds that we designed to. The worst of those cases is 52 seconds. So in case 6, after 52 seconds, visibility and thereby toxicity criteria were completely gone. That's summarised very, very quickly there. Essentially what we found is that the correlation between the failure mode and the ventilation condition is key. Where we have only air conditioning running, we lose tenability due to temperature. Where we open the doors, other way around, where we open the doors, we lose it for temperature. When we keep it as an isolated closed system, visibility, toxicity is our driving factor. Very last slide, I have to put it on because Joel's there and I promised him he would. Joel's on the screen there. He's doing the next part of the work, and what we're looking at is not just fires on suitcases, but what's inside suitcases. Because you can take anything on an aircraft, not petrol and motorbike batteries anymore, but clothing and all those things. So we're going to add in a variable related very heavily to the contents of those suitcases, and we're going to continue this work for the next few years, I expect. So, I'm over by 53 seconds, do apologise. 53 seconds less of questions, but I'm happy to take questions.
Thank you, Joe. Thanks, Joe. That's a really interesting talk. One of the questions I had on the toxicity front is what criteria we're using? Because if you're using like CO, a lot of times it's like a dosage criteria, and we consider it as instantaneous, but it's going to be pretty hard to fail a dosage one in 90 seconds.
Yeah, so in all cases we lost it because of carbon monoxide, so it was CO. We were doing the full fractionally effective dose, and we were plotting all sorts of things, but we found really early that CO was our limiting factor. I anticipate that will change when we add in different suitcase materials and things like that. The data that we had was based off hard shell suitcases, so we knew what the products of those were. We've been down to the supermarket and been looking at what else we can buy, and there are all sorts of plastics and polymers and things. So we think probably when we expand this, and actually that's a picture of me. I'm looking at a picture here that I thought might be on screen. Oh, there we go. There's a picture of Joel now. So the picture is from our lab there where we're testing these things because we think toxicity, now we know it's one of our real driving things, is going to be what we have to build into the next stage quite heavily.
Thank you.
Follow up. There was a fire recently, and I forget where, in what airline, but there was a fire, and everybody managed to get off, but it led me once again to look at this 90 seconds, and I've always thought that was crazy. I mean, I don't know what real world can we get off an airplane in 90 seconds, but nevertheless, was there I don't know, usable information that could be used from that experience to help in your studies?
Absolutely. If it's the case I'm thinking of, it was in Japan, and it was earlier this year. Yeah. Absolutely. It's a really, really good study. In that case, what we know is that people stopped to collect their belongings because they didn't have sight or smell of the fire themselves. Okay. They were being told, there's a fire on board, you must evacuate. But everybody was, pre-movement was extended, I'll grab my case, thank you very much.
Okay.
Very different when you see and smell the fire yourself.
Okay.
When you mentioned there was a fire recently, there was also one this morning, which a friend rather unhelpfully sent me today saying, good luck for the talk, Joe, by the way, have you seen this? But there was one this morning with electronic cigarette vapes that went up on an EasyJet flight over in the UK. So there's case studies even today coming out. But yeah, the Japan one is really key for human behaviour.
Yeah. Okay.
Thank you.
Sounds like then they need an odorant that smells like smoke that they can dump through the ventilation system to get everybody to move, not artificial smoke. Yeah. Oh, okay. I have a couple more.
Just a question for me thinking about this, but it's really fascinating talk, so I really enjoyed listening to it. But focus here is on, ASET, RSET with the case where they actually can egress. Is there any different thinking about, in-flight fires? I mean, I assume you have all these same problems that the, available safe time is very short. So how do we protect, or can we protect? I mean, I've gone through pilot training too, and in a little plane, it's like, oh, if there's a fire, you get down really fast, but that's not always an option at 30,000 feet. So I was just curious, what are the other fire, mitigating approaches in a commercial situation?
Dr. Pepper is really good at putting fire out. And we rely on our cabin crew to get hold of something that's on fire, like a laptop or an electronic cigarette, very quickly put it into a metal box and douse it with anything they have available, which is what they've got on the cart. Dr. Pepper, Coke, Fanta, whatever's going on. And that genuinely that isn't a joke, I promise you, is the training that's provided, because that is doomsday, 30,000 feet, a fire happens in the passenger aircraft, what else do you do? We had, at the airline I worked for, metal boxes, we brought these in, you put them in, you douse whatever is in there, and you fill it, you douse it with whatever you possibly can. Yeah, prior to that it was Halon and Freon, and we're not going there again, so yeah, that's exactly what we do. Yeah.
There's a question online about how can we achieve 90 seconds RSET, including the detection time and pre-movement time, taking into consideration the seatings should be considered a queuing plan, which will increase pre-movement.
Yeah, I mean, I don't really have an answer other than, I know, right? Like, that's what I say. That's why I'm doing the study. I don't think that you can have a standardized 90 seconds. If you do need to do it, use your own staff. It's very helpful. That's what I did for years. But in truth, yeah, the 90 seconds is not, I believe, and from the results that we're getting, a valid prescriptive number that you can use. Even in the event, I want to go back to Kevin's point about human behavior. Even the best drilled people in the world, you put it in a panic situation, and there can be no greater panic than a fire on board an aircraft at 30,000 feet, or even on the apron. Building the human behavior, your pre-movement is completely gone. So 90, I think, I don't think I'd have evacuated 20 people in 90 seconds when we'd stripped it out and used it for special service sometimes. So yeah.
Another one, maybe you said it, but how do you simulate the air conditioning?
Yeah, so we at first used a full HVAC system that we'd built in, and it just created more problems than it solved, in truth. So we ended up just having an inlet and an outlet for these particular models. That was after we'd realized we were most interested in diluting. So we were interested in the dilution of it. We simply did it with vents at high level and at low level. So extracting below the seats and tipping out from above. We had to have really, really fine cells for this whole model just to simulate the curvature. So we were able actually to have really quite small vents in our model, which were simulating those small aircon units you get. So simply airflow, vents in and out is what we went for. We do have some more complex HVAC models, but more problems than it solved sometimes.
Interesting, okay. Is there any consideration for like handicapped or disabled population or demographic?
Not in the 90 seconds. Again, I don't have an answer other than, yeah, I hear you, yeah, exactly. The 90 seconds doesn't take account of that. No, it's just a blanket 90 to evacuate in any scenario.
And what was the driver behind reviewing visibility as a tenability criteria? Does the CAA require its assessment? And if so, what is the failure criteria? It seems extremely onerous to consider this in a cabin fire.
Yeah, visibility is an interesting one. I'm glad somebody's picked up on that. We used it not for visibility. It sounds like a typical answer from me, doesn't it, where I've got a weird, quirky answer. It was a driver for toxicity, and it heavily impacts, we believe, the movement time of occupants. Because we think as visibility decreases, people drop down, and in fact that's what they're told to do. And we think that even more heavily leans into this 90 seconds not being linear. Because as people are crouching and they're moving, we think more slowly, or we know more slowly from it. It's why visibility became a criteria for us. So unlike in a building where we would use 5 meters or 10 meters visibility, we were doing that for toxicity. What we were actually looking for is the clear layer height. So in terms of visibility, we're interested in at what point do we still have clear layer maintained, which, as I've shown and demonstrated, very quickly becomes floor level because of this dilution factor that they're doing.
Okay, another comment, aircraft is a small place. Can it be divided into 2 compartments or multiple compartments?
Yes, it can be. It isn't typically, certainly not for this particular aircraft. There is a study from many, many years ago on a much larger jumbo jet, and they tried to drop in a curtain, a flexible curtain that you'd put in and you'd separate, and you would hold passengers in one compartment whilst the other compartment is allowed to continue to be involved in fire. That didn't go ahead. I think it warrants more research, because that might be a mitigation for us during a fire that happens at 30,000 feet, because we need something designed in. So it's not common, but it is a design that I personally think could work. So there is some work in that area, but it's not something that we see on aircraft.
Yeah,
routinely.
I guess to clarify, they said not complete compartmentalization, at least 2 smoke reservoirs or something overhead. Yeah.
Yeah, the smoke reservoir model was developed by Boeing, I believe, for some of the jumbos many, many years ago. I think it warrants some work, because you can hold more passengers than there are seats for a temporary period, certainly if you're flying to a local airport. So possibly, yeah, but not common at the moment.
And then final question, are there any safety factors applied for ASET and the RSET comparison?
As a general rule, yes, of course. Now, for us in this study, if I'm given the 90 seconds as a CAA regulation or FAA regulation, I have to assume there is an implicit margin of safety in that. Now, I should never assume, none of us should, but yes, I would often use a margin of safety. It's not acceptable for me as an engineer that the second after everybody gets out, the building collapses or the plane explodes or whatever else might happen. So yes, there is and ought to be a safety margin in there, for sure.
Okay, that's all I see here. Anybody else in the room? All right. Thank you, Joe.
Thank you.